Hello everyone. Today we enter the time series section of our course, which deals with observations that are ordered by time. In fact, it's really hard to not deal with time series data when you're dealing with econometrics. For instance, most of the macro econ data are time series data. GDP of a country is not just reported for that year, it has more meaning when you compare it with its previous years. And in fact, the order of that is important too. So you compare your GDP with the year before that, and that one with its previous year, and so on, rather than just shuffling your data and then look at that GDP. You're losing information if you shuffle your data because there is some information in the ordering. It's important what comes first and what next. Also, remember that order is important, but the time itself doesn't have any other value than just giving you the order. So don't don't really question the causality of any process in time series data because of the variable time, because that's just something defined by us. But you can question causality of some variable by the value of that same variable in the previous unit of time. Well, there's this definition when we work with time series named stationarity. Time series variable is a stationary if it has constant mean and constant variance. So both conditions should be satisfied. If just one of those conditions is not there, then you don't have a stationary process. And if you don't have a stationary process, you cannot run linear regression analysis with your data. Because when you want to run linear regression, you need to have error terms that are IID with mean of 0 and constant variance. But if you don't have that constant mean or constant variance, you're violating that condition. So just like the case of heteroscedasticity, your model output about your standard errors that creates your t-test, your f-test, your confidence interval, your r-squared, all those stuff going to be misleading, and you probably get significant results when you should not, and vice versa in these cases. So when working with time series variable, if we have non-stationary terms, then we end up to have non-stationary error terms, and non-stationary error terms is violating our OS assumption. It's easy to show that. Imagine that if we imagine that we have this model that we have yt that is modeled by two other factors in time. One is x1, the other one is x2. So the values of x1 and x2 at any time in this model are affecting the value of y. Now, if you rearrange this formula in a way that we have bring these guys to the left side, and we have yt minus that, we have the error term equal to this that you see over here. Now, if just one of these guys is non-stationary, since we can show that if having a non-stationary process dominates a stationary process in combination, and overall the linear combination of them going to be non-stationary, this right-hand side going to be non-stationary, and that means that the error term is non-stationary. If error term is non-stationary, then it's not constant mean and constant variance. Then that means that we cannot trust the results of our model, and we're going to have spurious results. Talking about spurious results is really interesting. If you guys search this term, search spurious correlation in Google, and this is one of the first links that comes up. This is spurious correlations by, and this website, if you go to the website, these are some interesting examples that it shows non-stationary variables that are completely irrelevant to each other, but you can find significant correlation between them just because you have not cured them for their non-stationarity. For instance, this is in the first one we have US spending on science, space, and technology, and suicide by hanging, strangulation, and suffocation. And you can see that there is a correlation of 99.79% between those two variables. Another interesting one is number of people who drowned by falling into a pool, and films Nicolas Cage appeared in. Uh, there are a bunch of other interesting examples that you can go and look into, and of course you can go to the website. There's a book about these stuff too. You can check it out. So that's the reason for that is we cannot trust that correlation factor anymore because we are not really respecting the assumptions of linear regression, which needs to have the error term coming from mean zero and constant variance. As a result of that, we're going to have misleading standard errors. Misleading standard errors give us wrong t-test and f-test values and wrong r-squared, and the model could look like to have a good fit, but actually it's and has a statistical significant relationship between the variables, but in fact the variables are not related at all. Just like the examples that we saw here. So in order to fix this problem, we need to transform our non-stationary variables to stationary forms. One of the main solutions that we have is taking the difference of that variable. For instance, if we are working with x of t and x of t is non-stationary, if we difference that series, that is like subtract xt minus 1 from that, and then we create delta x of t. Similarly, delta x of t minus 1 is xt minus 1 minus xt minus 2. And then we can check whether the difference is stationary or not, which in a lot of cases is stationary. We talk more about that later. So, for instance, here we have the similar equation that we had above. Let's just imagine that yt and x2t are non-stationary variables. Now we know that because they are non-stationary, we cannot really run this model because the E of t is not going to have constant mean and constant variance. It's going to be non-stationary. So we need to convert the non-stationary variables to stationary variables. Suppose that if we difference them once, they turn into non-stationary variables. So yt turns to delta yt, it's going to be non-stationary. It's going to be a stationary, and x1t that is non-stationary is a stationary. X2t that is non-stationary. If we difference it turns it to delta x2t, then it's going to be stationary. So x1t was stationary to begin with. Now we can deal with this new formula that we have here, which is delta yt stationary, beta 1 x1t stationary, and then beta 2 delta 2 x2t is stationary too. Now we can run our analysis. So this is what we need to do. But before actually doing this in practice, we need to learn how to detect non-stationarity. So what did we do to figure out that YT and X2T were non-stationary, and we had to difference them. That is that gets us to different tools that we can use for detecting non-stationarity. Like any other test that we do, we want to always have visual inspection, because just one number or summary measurement is not always telling the whole story. Um, not all tools and methods are 100% accurate. We will see an example of that today. So if we just trust one method, we might have a wrong inference. That's why we need to use two or three different ways to detect non-stationarity. So one is just plotting the time series. We can look at the time series and then see if visually we have constant mean and constant variance. If that's happening, then we're going to be okay. If not, then uh, if we see an obvious pattern of non-constant mean, non-constant variance, then we know that we are dealing with a non-stationary process. Um, Also, sometimes based on the nature of the variable that we are dealing with, we know that whether we have a stationary process or non-stationary process. For instance, if I look at the GDP of United States, I know that the average of GDP for past 4 years is way different than what it was 40 years ago. So I know that this this variable has been changing and kind of increasing over time. So the average of that has been increasing too. So it doesn't have the constant mean. So I know that it's a non-stationary process just by knowing about the domain of that variable. Similarly, if I want to think about the rate of the GDP growth, which is, for instance, maybe a year is 5%, another is 2%, 3%, then I know that that variable is more or less a state following a stationary process. It's bounded. It's not going to have uh, perhaps very, very large numbers or very, very, very small negative numbers. So that variable will come from more like a stationary process. Or if I want to think about unemployment rate, that's more like something that is coming from a stationary process. Generally, I'm saying generally, not all the time. It really depends on with the example that you're working with. But most of the variables that we deal with, if we're at their level terms, like GDP, then we call them, they are likely to be non-stationary. But if they have rate or are coming from some definition that is similar to rate, then that ends up to be usually stationary. We will talk about this a little more too, and we will see some examples of it. One rule of thumb to figure out whether you have a stationary process or not is that you calculate the standard deviation of your variable and then difference it and then calculate the standard deviation again. If the standard deviation drops by a lot, like a half or more, so if the difference were more than twice, then you know that you have a non-stationary process. But if the difference was not that much and it was less than two factors, then you know that you have a stationary process. One of the most famous methods that are being used out there is the ADF method, augmented Dickey-Fuller test. It's very important to remember that ADF tests have relatively low power. At the end of this video, we will show an example of it. So if you have a large number of observations, it's easier to trust its results. But if you have low number of observations, you cannot really just trust the results of the ADF test. That's why we are saying that we have to do multiple sorts of inspection, like do the standard deviation calculation, visual inspection, and the ADF test. That's that makes it more makes your inference more confident if all three are kind of telling you the same story. Also, you can look at the autocorrelation functions. The autocorrelation is its own topic that we're going to talk about in time series, but there is a package that we're going to use to test these stuff and test for non-stationarity. So in that we will show visual representation of autocorrelation functions and get familiar with it more. So as we said, transferring variables into stationary form, one of the main way to do it is differencing that variable. And just like how we showed it over here, delta x of t is value of x at that time minus the value of x at its previous unit of time. In R, the diff function does that for you. So if you give a time series to the diff function in R, you can get the difference of that on the left-hand side. Now we need to define our test for non-stationarity, specifically the ADF test. For that, let's talk about this simple dynamic equation. So we have yt and yt minus 1 because we have the time value, the temporal index there. We have a dynamic process because the value of y at time t is dependent on value of y at time t minus 1. And we have this coefficient here of coefficient phi. If the absolute value of phi is less than 1, we know that over time, this whole series is going to kind of converge to 0. Because you start with some value, the absolute value of that is less than 1. So let's say, for instance, half. So the first time if you start with 1, the second time you'll be half, and then next time you'll be 0.4, and then keeps going down until you're very, very close to 0. On the other hand, if that value is greater than 1, every time you are multiplied by a number greater than 1, and that means that every time we're getting larger and larger and larger, so over time you kind of reach infinity, and this is an explosive process. But if the absolute value of that is equal to 1, you either stay there or oscillate if it's minus 1. Now let's imagine the same thing but adding some noise to it. So now it's a dynamic equation but in a stochastic process. It's not deterministic. Here it was deterministic because there was no noise in the equation, but here by adding the noise we have a stochastic process. The noise here is having mean of 0 and constant variance of sigma 2. Now, more or less, same stuff gonna happen. If if we have a phi greater than 1, then we're gonna have an explosive process, and then if we have a phi less than 1, then we're not gonna we will have a bounded process and not gonna have an explosive process. So what we want to do is we kind of want to estimate the value of phi, because by knowing that where phi lies, we can figure out whether we have a bounded process or an explosive one. Because if we have a bounded one, we know that we have a stationary process. Otherwise, we have a non-stationary process. That gets us to unit roots and a stationarity. If we imagine that same equation that we define up there, and if we want to estimate the value of phi, we can show that And the absolute value of phi could have a one-to-one correspondence with uh, a stationarity. So if the absolute value of phi is less than 1 or lies inside the unit root circle, then we say yt is a stationary. Otherwise, we say yt is non-stationary. So it's we don't really run into situations that are explosive. You can easily recognize an explosive process, so that this is not going to be the case for us. So the remaining cases would be phi equal 1 versus absolute value of phi less than 1. If if this is happening, we know that we have a stationary process, and if this is happening, we know that we have a non-stationary process. So we define our null hypothesis as H null is absolute value of phi equal 1, that is non-stationary, and H1 is absolute value of phi less than 1. So if we reject the null hypothesis, we know that we have a stationary process. Otherwise, we cannot reject the non-stationary null. So looking at this equation above, right there, if we subtract yt minus 1 from both sides of this equation, yt minus 1 give us delta yt on the left-hand side. And on this side, when we have yt minus 1 subtracted, we end up to have phi minus 1 multiplied by yt minus 1 plus e of t. We can call this phi minus 1 gamma, replace it by gamma. So our equation would be delta yt equals alpha plus gamma yt minus 1 plus et. Now, if we substitute phi with the gamma, we end up to have phi minus 1 is equal gamma, so phi is equal gamma plus 1. So gamma plus 1 is here, equal 1. That 1 and 1 going to be cancelled. So your H null would be gamma equals 0 versus gamma less than 0. And that would be basically the ADF test. So the ADF test is creating this equation and checking whether this coefficient is equal to 0. Why did we do that? Because in linear regression, we are estimating coefficients, and the null hypothesis for coefficient is usually equal to 0. That's why we made that variable transformation. And in the special version of ADF test would be, uh, I'm I'm sorry. This would be the Dickey Fourier test. So, and then the augmented Dickey Fourier test is an improved version of Dickey Fourier test, which is adding more lags of delta yt to the right-hand side. But still, the null hypothesis is gamma equals 0 versus gamma is less than 0. We know that if gamma is less than 0, that means that phi minus 1 is negative. That means phi should be less than 1. That means that phi is falling inside that unit root circle, so it will be stationary. Otherwise, it would be non-stationary. So if we run the augmented Dickey Fourier test and ends up to see that we have a significant gamma, that means that gamma is non-zero and is negative, then we know that we have a stationary test. Otherwise, we have a non-stationary test. The 10% critical value for augmented Dickey Fourier test is minus 2.6. It's a bit different from what you were using in uh, linear regression, but it is still a t-test. Um, Also, when packages want to figure out what number of lags they need to use on the right-hand side of the augmented decay Fourier test, they use BIC or AIC factors. So some could use AIC, some could use BIC. That's why some packages could end up with different values when they're estimating the ADF results. And as we mentioned before, if we want to see that we have a stationary variable, we want to show that we have a significant result for gamma, and gamma is negative, having a negative estimate. That's when it makes sense that phi is non-zero and is within the unit rule circle. We have this definition of order of integration. So if we have a non-stationary variable, that variable has constant mean and constant variance, we say that variable is integrated of order of 0. That is I0. So if we find that variable that is not stationary, for instance, yt, if it was not I0, and if we figure out the difference, then the difference would be stationary, then we know that yt would be integrated of order of 1 and I1. Otherwise, it might be integrated of order of 2. It's really hard to, in practice, to find something with order of integration greater than 3. We can definitely have, create it in our simulations, but it's very rare to find something in practice with order of integration greater than or equal to 3. In some econometric models, we have models that are using time trends on the right-hand side. So they could um, define the time series variable as a function of time. Again, it's really hard to physically imagine that something is happening because of time, because time is just something that's defined by us, and it doesn't have anything to do with the physics of any phenomena. It just has to do when we are observing that phenomena, and it's just something that is related to the observation part rather than data generation part. So it's it's um, it's not really suggested to use time trends in your um, right-hand side variables, except some specific times in practice, like one example that you saw in your assignment. But usually, if you can find a better way and not doing something like that, it's definitely more sensible. Anyways, one thing that they talk about when they're talking about stationarity and time trends is that whether a variable trend stationary, that is, if you get the time trend out of it, the variable would be a stationary. And that is kind of like you have a deterministic trend that is giving you the time trend part and a stationary variable, and then together they give you the trend, the stationary variable. And we would see a few examples of them down here really soon. Also, one library that we're going to use in R to help us detecting non-stationarity is Intord. I will tell you how to install that. It's a bit different from other library installation that you had. So once we are we want to work with time series, we don't want to do this. We don't want to detrend anything to get the stationary variable. What we want to do if we find non-stationary process, whatever the cause could be, might be the time trend. What we want to do is just differencing, because the differencing going to solve the problem, and we will see that um, how actually that works and in simulation and also mathematically. Let's look at this data generating process of having yt being a function of its previous value, and also we have this beta with t that is giving us the time trend term, and of course we have a constant mean, constant variance for our error term. So in this example, we are using 0.8 for our phi, and beta is 0. So in the first example, I said beta 0 and 0.8 for phi. We know that 0.8 is less than 1, so this process should be stationary. This is the code to create this process, and then we can look at the results. The results completely look stationary. We have a variation, but we can see that the variation is kind of bounded, and then it's around a constant mean. It's around a line around maybe 0. Now we do the same thing. We don't have a time trend, but our phi is now changing to 1. So using the code here, but changing phi equal to 1 instead of equal to 0.8. Now I'm going to have a non-stationary process, because as you see, I don't see the same pattern that I had in the previous plot. It doesn't seem that I have a bounded process. The process was going up and down here, and then out of a sudden jump to another levels, and it kept going up over there. Totally different process when we compare it with this one. Now I want to have a trend stationary process. That is, I have a stationary part, and I add a trend part to a time trend part. Looking at this, it looks non-stationary, but in reality, it's a trend stationary. That is just, if I rotate this by 0.1, slope of 0.1, which is what's happening with that t thing, I'm going to have a stationary process. Now, if I have a non-stationary process with a time trend, then things going to get even way worse. It's super non-stationary, you know. Here I have non-constant mean and variance. Same thing here. It's just a more extreme case of it. Now let's look at what's going to happen if we difference stuff instead of detrending. So here is the equation that we had, and I'm not assigning any value to them. Let's imagine just parameters beta and phi for that. Now I have for yt, if I write the same thing for yt minus 1, yt minus 1 would be alpha plus phi, yt minus 2 plus beta, t minus 1 plus error term at t minus 1. If I subtract these two equations from each other, I have delta yt on the left-hand side, and then the right-hand side of that come here, and then this one going to be subtracted here. Alpha and alpha are going to go away. I have phi yt minus 1, phi yt minus 2, so it would be phi multiplied by yt minus 1 minus yt minus 2, that's delta yt minus 1. I have beta t, and here I have minus beta t plus beta, so beta t's are gone, and then I have plus beta. So plus beta is kind of my new intercept, and I have error term time t minus error term time minus 1, t minus 1. They're IID, so if I call this two terms together, E prime of t, that would be distributed coming from the same distribution too. So would be mean 0, and it would be a normal with mean 0 and constant variance. So no more time trend we see here. There is no t here, just like when we started we had t, we don't have it at the end. So differencing took care of it anyways. So we difference it and everything's fine. We didn't have to think about detrending stuff. Here I have a code for simulation. Let's talk about this. We want to show how ADF test could be misleading. I go to my sound box. And just open one of these. Run this line. So library T series, if you haven't installed it, install that. It gives us functionality of using ADF test. So I want to run that. I'm setting some seed because I want to be able to create these results. So I haven't had that installed here. So I go to library and then call T series. So when you're in CRAN, that means you're installing something from online repository. So it goes out there, installing the package, and get done. Now that we are installing the stuff, let's install Intward too. To install package Intward, you have to first download it, and after you downloaded the package, because it's a .tar.gz package, so it's a zip one. You first have to select that, and then you need to go to the location that you have that saved. The name of the file is intward underscore 1.01 targz. So do that. Now we are installing something from the local directory, and then install it. That is installed, getting installed too. So now I have both of them. So library T series, setting some seed. Now I want to run simulation for a case that I have 25 observation, 50 observation, 100, and 1,000 observations. And I want to give 5 for value of 0, 0.5, and 0.8, and 1. So for the first 3, I know that it's a stationary, and 1 would be non-stationary. I do every case of this simulation 1,000 times and just calculate. These are the steps of the simulation, and then it gives me some y, and then here I'm doing the ADF test from the T-series package and get the p-value from that. And at the end of this loop, I can look at all the p-values and calculate how many times the p-values, for instance, were less than 5%. So if it was less than 5%, I reject, and if it was greater than 5%, I fail to reject. The null was non-station. The null was, the null is non-stationarity. If I get low p-value, I reject non-stationarity. And at the end of the simulation, I calculate how many times I reject non-stationarity. When I have a stationary process, I want to reject non-stationary. So for these 3 ones, I really want to do that. But when I have a non-stationary process, I don't want to do that. Now, if you go back to this file, you have this link at the bottom, which if you click on it, you get to this visualization of the results that we ran. Here, I have the number of observations showing every test by color. So for the test that I had 25 observations are blue, 50 observations orange, 100 observations red, and then green is 100,000 observations. As you see, when I had 0, 0.5, and 0.8, that is when I have a stationary process, I need to reject the non-stationarity all the times. When I have 1,000 observations, it's easy for ADF test to do that. So 100% of times doing that. When I have 100 observations, when phi is small, it does 94%. It's good. But even for 0.5, it's accurate 75% of the time. So the power is 75%. And 32% when it's 0.8 as it gets closer to 1. So you can see that ADF test is just losing its power when number of observations is low. Even 0.8 is not really a high number, but it's still hard for ADF test to detect that. When number of observations is 25, it's just the power of ADF test to detecting or rejecting non-stationary at 0.8 is 8%, which is not really good. So that was an example of showing the low power of ADF test. Now we have another example here that we want to look into. Let's look at this simple unit root example. Here I have number of observations 100, so I run that, and then I want to create a stationary time series, so it would be just normal with constant mean and constant variance. So if I just create 100 of them, and if I plot it, I can see that, yeah, it's pretty stationary. Draw the mean, which is around 4, and draw the line on 4 itself, so you see that they're very close to each other. Now, what if I want to create a non-stationary process? I start from some initial value x0, and then I want to, every time, because non-stationary, I have a phi equal 1 multiplied by that plus some error, and that's going to have my create my next value of x and so on till I do it 99 more times, and I have a non-stationary process. I want to use library intort, so I run call the library, and if I say intort function gives me that. Looking at that function, I can see that the a stationary process, the standard deviation is 9.22. I difference is 13.7. So the difference of them is not more than twice. It's less than that. And I also look at these ACF functions. I see other than the 0 time point, especially in the first one, I don't see anything crosses those blue boundaries. I see the results of the ADF test. My for y is minus 10.58, which is way smaller than the critical values that are shown here. Same for delta y. So both of them are stationary. I don't need to difference my stationary process based on these results because it is stationary. But now let's do the same thing for x, which was non-stationary. Looking at the results, we can see that it's 2.31. This is 1, so more than twice difference between the standard deviation values. I can see that the lags in ACF are greater than those boundaries. The critical value is minus 2.62. In this case, is a little smaller than the 10%, but not but larger than the 5%. So putting these things together, I can although with 10% significance value, ADF test wants to imagine that this is a stationary, but altogether I know that this is non-stationary. I need to difference it. So if I difference it and then intort that one, I look at the new results, and now the new results is standard deviation 1.5, so less than 2. The rule of thumb for a standard deviation tells us the y is stationary. I don't see anything out of bounds there. This is minus 10.87, way smaller than minus 2.59 or minus 3.51. So Now the difference of x is stationary. So x was I1, and we change it to I0 by difference and get ST was I0 to begin with. One more quick example is we have this Fed data. Open the Fed example is coming from Federal Reserve Bank data. We run that. We have date, saving, and income. So we have saving, disposable, and disposable income. I do the parameter row to get the plots in one view. I'm plotting the income, so that's a variable income. And then I plot the savings. These are macro variables, and then I can run summary of M1. Here we can see that visually these guys are non-stationary, so it's similar to that spurious correlation website examples. I'm gonna find relationship between these two no matter what, but that relationship is not really meaningful because I'm gonna violate the assumptions by using non-stationary variables in this case. So if I run the summary, if I run that model and then run the summary, I get some results, but this I cannot really trust them. Let's run library intert saving. Looking at this, it's easy to figure out that this is non-stationary. Do the same thing for income, and similar results for income as well. And now that we rejected uh, now that we are seeing that this is not the stationary and it's non-stationary, we need to difference those variables. It's also run this again. Let's get the plot of the residuals of the first model that we ran. It doesn't seem like having a constant variance, at least. So we run the differences. Now let's intort the differences. It looks better, and I still see some sort of non-constant variance, so some better things could be done to this. We talk about this later. Maybe if you take the log of these values first, you end up with better results, but it's much better than what it was before. So by differencing, we solve a lot of the problem. If you look at the standard deviation, they're very closer to each other now. Same thing for income. Now the difference of income is a stationary too. We can see that the critical value is very smaller than these critical values from the significance levels. So we are having a stationary process. Now, if I model these two stationary processes, I can trust this model too more. I can see that the rate of income, as it grows, it has a positive effect on rate of saving. If I look at the residuals of model 2 and then run residual model 1 again, I still could criticize model 2 residuals. Maybe I have non-constant variance here, but the case of non-constant variance is way more extreme when I didn't difference. Still, our job is not over yet with this model. This model could get improved. We haven't included any lags. For instance, saving today should your rate of saving today should be dependent on rate of saving in the previous years or previous days that you had. So and we haven't included any of those lag terms, which are important. But that would be a topic for next videos. Thanks for watching.